Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our thermodynamic lecture series. Today we want to look at unsteady heat transfer processes. So when we are using the word unsteady, we are talking of unsteady state heat transfer processes. We have talked about steady state heat transfer. We have said that the rate of heat transfer was constant. And when you talk about those surfaces which are perpendicular to the direction of heat flow, then we say that those surfaces were isothermal. In other words, the temperature in those surfaces were constant. This is not the case with unsteady heat flow. In unsteady heat flow, if you do the temperature profile, you're going to see that the temperature varies. The temperature varies. In the case of unsteady heat flow, from the temperature profile, it will be observed that there is variation. There is variation in temperature. And so, good examples of this would be, for example, the heat transferred across the cylinder wall in an internal combustion engine, and also, for example, heat transferred across the walls of a furnace during the cooling or heating process in a furnace. So, good examples include heat transfer across cylinder wall in an internal combustion engine, or heat transfer across the walls of a furnace during cooling or heating process. Now, a very classic example which we'll use to illustrate unsteady heat flow is the cooling or quenching of a billet. What is a billet? A billet is a semi-finished product. In other words, it still needs further processing to give you the products. So when we cool this billet or quench it in a cooling bath, I don't want to talk about reservoir, because a reservoir is like a sink, so that even if heat is transferred into it, it should not show significant changes in its temperature. So I'll talk about cooling bath. So if we cool a hot metal billet in a cooling bath, then we will be able to come up with the illustrations and expressions on unsteady heat flow. So a classic example, a classic example is cooling or quenching a hot metal billet in a cooling bath. Cooling bath. What's a billet? No, it's not. This is a semi-finished product. Requiring further processing to obtain the product. Now, a billet can have any shape, any geometrical shape. It can be a square, it can be rectangular, it can be a circle, and we're going to see why the shapes are important. Can have any shape, be a circle, can be a square, can be a triangle, etc. And so let us assume certain physical properties for this particular billet, for the billet. One, we are assuming that when the billet is put in that cooling body, when we put it in the cooling body, let's say we have the billet here, put it in the cooling body. This is a cooling bath. So we have a coolant, and be any coolant, whatever coolant you want. Can be any coolant. It could be an oil bath, it could be a water bath, a coolant. So let's just say that the temperature T1 here and the temperature of the bath here, of the cooling bath here, T1 is definitely greater than Tc. Because you say there must be a temperature differential for heat to be transferred from one body to the next body. And we are assuming that the heat lost from the billet will be equal to the heat gained by the coolant of the cooling body. And so let's make some assumptions about the physical properties of, or physical characteristics of the billet. Some assumptions about the billet. Of the billet. One, we can say that its volume, assume its volume is V. And its density, we call it rho. Its heat capacity, we call it Cp. The surface area, A, and its thermal conductivity, K or kappa. So we're assuming those are the physical properties of the billet. Assuming those are the physical properties of the billet. Now, we are talking of heat transfer. So straight away, we can pump in, we can move in and use the Fourier heat laws in our system. The heat law in our system. So, the heat lost by the billet will be given by density and mass times the heat capacity and the change in temperature over the interval of the process. The tau there is the interval of the cooling process. Interval of the cooling process. Now, when we put the billet in the cooling body, heat has been transferred from the billet into the cooling body. So if we assume that the transfer coefficient for that, heat transfer coefficient for that process, let's call it H, then applying the Fourier law, we know that that quantity, the heat transfer coefficient, and this times the area of the transfer and the change in temperature will give us that expression for the rate of heat transfer. Remember from Fourier's law, heat law, we say that dq was minus k, thermal conductivity area, and then change in temperature. And so if we say the transfer coefficient, the heat transfer coefficient for the heat transfer process from billet to the cooling body, or cooling bath, is H. says H. Then it means that dq, which we have seen is given by the density, volume, heat capacity, the tau over the tau will be equal to minus the overall heat transfer coefficient in the billet and the cooling body times the area of flow into this particular change here, which we have is the change in temperature. That's the temperature of cooling body and its initial temperature. So Tc is the final temperature of cooling body and T is initial temperature. To make our life easy, I can call that Tc minus T. Let me just call it theta, change temperature there. Now, let us now put in some of these quantities which we have assumed. Let's put in some of these quantities which we have assumed. See which is a better pen. We have then dq. That looks better. It's a much better pen. So we have dq is equals to rho VCP. Change in temperature now, we have called it theta, d theta, over the time interval. That should be minus HA theta. So if we rearrange these equations and integrate, I'm going to use several identities. You need to look at I encourage you to look at our earlier lectures. We say that's the natural log theta plus c. And also we say that if we have your x, that would be x plus c. That's just the integration constant. The c is integration constant. And if you put the limits, then you don't have to worry about the integration constants. You don't have to worry about the integration constants. So I'll use these identities here. So let's rearrange on rearrangement. On rearrangement, we will have rho v Cp the theta over theta is equals to minus H A the tau. So integrating on integration, we'll have rho the Cp integral, some initial value, some final value, theta over theta is equals to integral minus let me put this out, minus HA integral from some 0 tau the tau. Very simple now. Let's apply the identities which we have talked about there. We apply the identities. They are very simple identities. We have just said d theta over theta integral of that will get natural log. And if you integrate that, you simply get x. So in the same way we get tau here, we'll get natural log. So we'll have rho VCP natural log of theta over theta naught is equals to minus H A tau. Remember, assuming that tau naught is 0. So that's the time interval for that process. So the initial time will be 0. So if we use the identity, that natural log of y is equals to m implies that y is equals to e raised to power m. So we can simplify that and simply say that if we reorganize these quantities, the natural log of theta over theta naught is equals to minus HA over rho VCP tau. Therefore, we have theta over theta naught is equals to minus e to the minus HA tau over rho VCP. This e needs to be a little bit down to show that it's an exponent. Raised to that power. Now, why did I say the geometry of the billet was important? If you look at here, there is expression for area and volume. Area and volume means that the geometry is important. Because you have area and you have volume in that expression. So the geometry is important. For example, the area of a circle is pi r squared. That's not the area of a cuboid. And the area of a triangle is not pi r squared. So the area and volume, whenever they appear, that means definitely that the geometry of that unit or system becomes important. So let us look at further simplifications which we can have in terms of our expressions here. Look at further implications. Let's look at further implications. Now, we had said that these quantities here, theta, natural log of theta over theta naught is equals to minus HA tau over rho VCP. Remember, we have said that the thermal conductivity of the billet is K. So we want to break down this expression because there's very important information which is hidden in this expression here. So we recognize one, that V over A is L, and two, that the thermal conductivity of billet is K. These are two things you want to have. So that if we reorganize this in theta over theta naught, then HV over KL, K, remember, the thermal conductivity of the billet will be given by K, we have over rho CP, we have A over V squared tau. So we have just factored in these elements. We have just factored in these particular elements which are important for us in breaking down this quantity so that we get some very important information in this particular system, here. Now, if we look at these particular quantities, we have already said V over A is L. So we can replace that with L. So that we have H L over K. And that's multiplied by K rho CP. This is V over A is L, so this is 1 over L squared. So that becomes tau over L squared. Now, breaking this up, this is basically that expression. But we have just broken it up. Just like when we were dealing with partial derivatives, we use the permuter and we use the inverter to break those partial derivatives into quantities which we know. Now, this is what we have done here in this particular process. this quantity here is the same as that quantity there. Only that you have factored in things. For example, if you look at thermoconductivity, if you remove it, you can cancel it out, for example. You can cancel it out. You cancel it out very, very easily. And so if you cancel this out with that, you'll just be left with A over V. So we have just rearranged it to get very important quantities from this particular expression. I repeat, this quantity here is exactly the same as that. We have just introduced the thermal coefficient of the thermoconductivity of the billet. So you can realize that we have introduced it. If you cancel them, if I cancel this out and I cancel this out with this particular one, I'll be left with these particular quantities. Now, what is this quantity here? This quantity is called the Biot number. Very important quantity. And this quantity here is called the Fourier number. So this is Bi symbol, Fo symbol. Now, if we look at the Biot number, when the Biot number is large, that means that this quantity, thermal conductivity, is small. And if thermal conductivity is small in the billet, what does it mean? It means that the internal resistance in the billet is high. Internal resistance in the billet is high. And of course, when it is large, when the Biot number is small, then K is large. So thermal conductivity is very large. So internal resistance in the billet is small, or the resistance in the cooling system is high. The cooling, the resistance, cooling bath, high. Very important for us to note that. Now, this quantity, K over O Cp, is referred to as thermal diffusivity. In fact, for example, in most cases, thermal diffusivity increases with the temperature. Plus is a small thermal diffusivity which ranges from 0.3 to 0.5. And for metals, it's relatively high, and the thermal diffusivity increases with the temperature. So if we plotted this logarithmic expression for that theta over theta naught versus the Fourier number, if you plot the logarithmic form of that versus the Fourier number, it's not drawn to scale. It's just a sketch to give you a feel of what we are talking about. And we'll get that. When the Biot number is 1.0, we'll get probably that. When Biot number is 0.5, we'll get that. When Biot number is 0.25. And this Biot number and Fourier number are very important quantities, and we are still going to meet them as we continue with our lectures. So we have still seen unsteady heat flow, which is not like steady state heat flow where the rate of heat transfer is constant and the temperature in those planes are constant, so we are dealing with isothermal surfaces and so forth. No, in this particular case, they vary. The temperature of the unit normally varies. If you do the profile, if you map the temperature, see that they vary. And so the processes are unsteady, they are unsymmetrical and so forth. And we have seen that when we have come, for example, You have seen that the area and volume matters for the billet, so the geometry matters, and these are very important things which you need to always note as you're solving some of these issues in heat transfer. So let's stop at that particular point.